Welcome to the Explainer. Today, we're diving into the hidden mathematical rules that govern how everyday things spread. It's a rulebook so incredibly fundamental that it actually dictates everything from subatomic particles right up to moving human crowds.
Picture this stark contrast for a second. Imagine a single drop of ink hitting a glass of perfectly still water. Over time, it slowly, lazily diffuses into this cloudy, fuzzy haze, right? Now contrast that with packing sand into a mold or trying to walk through a completely packed, dense crowd of people. The sand and the people, they actually physically push back. They don't just drift around randomly, they are forced outward in a very specific, highly organized way. Today we're exploring exactly what happens when things fundamentally repel each other. To unpack how this all works, we're going to track a cluster of particles through three distinct phases. We'll start with standard diffusion versus repulsion, move to phase 1, dense expansion, hit phase 2, semi-sparse growth, go into phase 3, thermal takeover, and finally look at real-world suspensions everywhere.
So, let's kick things off with standard diffusion versus repulsion. Take a look at the contrast here. On one side, we've got the completely chaotic, random walk of standard Brownian diffusion, literally just particles bumping around with zero agenda. But then contrast that with the beautiful, compact, radial spread of repulsive particles. It's completely organized, pushing outward almost like a synchronized dance. So, standard diffusion, it gives you this fuzzy Gaussian profile. Basically, it fades out infinitely into its surroundings, so you can never really pin down where the drop actually ends. But a repulsive suspension is totally different. It expands with a parabolic profile. It has strict, sharp boundaries. You could literally draw a solid, hard line exactly where the suspension ends and the empty space begins. To really get why this happens, we have to talk about the Pecklet number. Think of it kind of like the referee in this physics match. It tells us whether our particles are being driven by deterministic pushing forces, physical repulsion, or if they're just getting tossed around by random thermal noise. A massive Pecklet number, that means the pushing forces are absolutely dominating. A tiny one? Well, then random thermal chaos has totally taken over the game.
Which brings us to phase 1, dense expansion.
This expansion actually goes through a very strict three-step mathematical life cycle based entirely on time and the changing density. We go from dense athermal at T to the 1/4 to semi-sparse with log of T to the thermal takeover at T to the 1/2.
This timeline maps out the exact radius of our expanding cluster. Notice those distinct kinks in the graph? That's where the math literally shifts gears. We start way out in the athermal phase, which basically means the particles are packed incredibly tight and thermal heat isn't even a factor yet.
In this initial dense phase, I want you to think of a packed room where a fire alarm just went off. Everyone is shoulder to shoulder, frantically pushing multiple neighbors away all at the exact same time. The pushing forces completely drowned out any random thermal movements. And because of this massive multi-neighbor interaction, the suspension actually expands at a strict mathematical rate, proportional to time to the power of 1/4. It is a rapid, forceful blast outward that keeps a razor-sharp edge as it barrels into the empty space.
All right, let's shift to phase 2, semi-sparse growth. As the source material highlights, at intermediate times, each particle interacts only with its nearest neighbors, and there is a transition to the semi-sparse limit with a logarithmic dependence on time. So as the drop expands, things inevitably thin out, right? The particles are finally far enough apart that they aren't pushing against 5 or 6 neighbors at once anymore. That continuous crowded shoving match is faded into just a few discrete, localized bumps.
If you look closely at the math, you can see this shift happening in real time. Watch how the initial rapid expansion bends off into a totally different trajectory. That new path represents a dramatic slowdown into a logarithmic scaling.
So what's happening here in this semi-sparse phase? The chaos has transformed into a highly organized, but much, much slower logarithmic growth. Repulsion is definitely still the boss here, but the expansion is kind of running out of steam. Why? Because there are literally just fewer neighbors to push off of. That initial outward blast hits a massive speed bump and starts creeping along.
Which brings us right to phase 3, thermal takeover.
Now we hit the long time limit where thermal forces finally take over. The particles are so isolated out here that our referee, the Pecklet number, finally caused the match in favor of thermal noise. The classic random walk returns, and that beautiful, compact, sharp edge we had, it just begins to dissolve right back into a fuzzy blur.
At this incredibly low density, classical random Brownian motion reclaims its throne.
We've gone completely full circle. We are right back to the standard fuzzy diffusion we started with, spreading at a rate proportional to the square root of time, or t to the 1/2.
Let's wrap up with real-world suspensions everywhere.
You might be wondering, why does all this actually matter? Well, these exact rules aren't just abstract math on a chalkboard. They govern an unbelievable diversity of things around us. They dictate the consistency of the soy milk sitting in your fridge, how printing ink behaves when it hits a page, and how high charge density batteries manage their internal particles. It literally scales up to biological systems too, like bacterial colonies spreading in a petri dish, or how dense human crowds dynamically filter out of a packed stadium.
Understanding how things naturally push back against each other gives us the actual power to predict and even manipulate the materials we interact with every single day. Thank you so much for joining me for this explainer. I'm going to leave you with one final thought to chew on. If these simple mathematical rules dictate the shape of literally everything from microscopic particles to moving herds of animals, what other invisible boundaries are secretly shaping our reality? Keep observing, keep questioning, and I will catch you in the next explainer.